we continue with integrals that involve the use of the half angle substitutions. And this time around, we have the first question in that is here. I hope you had time to try it. So we're going to look at this problem here. So how do you work it out? And yeah, let's see how we proceed with that one. The first step is just to define what you're dealing with. So let t be equal to tan theta over 2. Here it follows that then d theta will be equals to 2 dt over 1 plus t squared. And then since we have both sine and cosine, we'll need both. So then sine theta will have to be equal to 2t. Let's see. Yeah, that is my d theta. So this will be 2t over 1 plus t squared. In the same way, cos theta will be equals to 1 minus t squared over 1 plus t squared. So now that we have everything we need, we can perform our substitution. So we're not dealing with the integral of 3 minus 4, where we have sine theta, we'll put 2t over 1 plus t squared. Then you have plus 2, where we have cos theta, we're putting 1 minus t squared over 1 plus t squared. Then finally we have d theta, and d theta is going to be 2 dt over 1 plus t squared. So now we just have to write this as a single fraction. So let's deal with the first part. So in the denominator, I want that to be written as a single fraction. Best part is the denominator here. In the denominator, it's 1 plus t squared. So the 3 will multiply the 1 plus t squared to give us 3 plus 3t squared, minus 4 will multiply that 2 to give us minus 8t. Then plus, now 2 will distribute there to give us 2 minus 2t squared. Basically, I've just multiplied this with all this. Then they distributed the minus 4 to multiply 2t to give us minus 8t. Then 2 multiplied 1, then multiplied minus 2 minus t squared. So that now this is all over the common denominator, that 1 plus t squared. Here we still have what d theta is, which is 2 over 1 plus t squared dt. So as a single fraction here, we know to say this 1 plus t squared goes up, so that it becomes over that 3. Now I can simplify this. The 3 and the 2 will add up to 5. Then I have minus 8t. Then 3t squared minus 2t squared will just give me t squared. Then multiplying 2 over 1 plus t squared. This and this will cancel out. The 2 I can keep it anyway. So I have 2 over, then I have t squared minus 8t plus 5 dt. So this is what I have to now integrate. So in most cases, whenever we use this approach, in most cases it results into an expression that you have to proceed by using partial fractions. In most cases, that's what you end up with. Here, let's see if we can solve this quadratic expression. There are two methods, the two things I expect here. If I can't get linear factors or repeating factors here, so that I get the partial fractions, then I would try completing the square. Not even try, then I would have to depend on completing the square. It will have to work. So let's try to factorize that. Factorizing by product and sum, I'll have 5t squared. Terms, when multiplying, you get 5t. Add, you get minus 8. I think I can't get any terms that fit that criteria. Multiply, you get 8. Add, you get 5. I think we can't get that. So since I feel like factorizing is not working, I'll resort to completing the square, since that one will have to work regardless. So I have to complete the square for t squared minus 8t plus 5. So I'll proceed to just saying half of the coefficient of the t there, which is minus 4. I'll square it, add it, then subtract it. Then we have plus 5 at the end there. So now we get t minus 4. And then minus this one I'll square to 16 plus 5. So that here you have t minus 4 squared. Then when you combine these two, you end up getting minus 11. So let's confirm again. So we have half of that, which is minus 4. So we square it, add it, subtract it. Then that is going to be 16 and so on. Okay, so we have completed the square. So to complete the square, we now have 2 over. So this is t minus 4 squared minus 11 dt. So we've ended up in this situation. Now, how do you integrate something that looks like this? So for this one, I hope you recall, we're going to let this whole lot here to be equals to sec. So let t minus 4, that's minus, yes, t minus 4 be equals to sec theta. So that when you differentiate now, dt d theta, derivative of 4 will be 0, derivative of sec theta, this is going to be equals to sec theta tan theta. That is going to be our derivative there. So that dt will have to be equals to sec theta tan theta d theta. So that now, when we substitute, we now have 2 over where we have t minus 4, that is just sec theta. Okay, so I think we left one thing there, the 11 there. So the 11 here, we have to get its square root. Remember, the substitution is whatever this is equals to a sec theta. So a is the square root of the 11. So we need to include that one there. So the square root of the 11. Since it's not a perfect square, we'll keep it as the square root of the 11 there. So that one will still be here even after differentiating. So this will be square root of 11, square root of 11. So that when substituting now, we're going to have square root of the 11 and then sec theta, all this squared, then minus. Okay, so then minus square root of the 11 squared, but that is just the same as just 11. And then next we have dt. So where we have dt, we're putting root 11. Then we have, so that's root 11. Then we have sec theta tan theta d theta. So that from here, when we square, we have 2 over. This becomes 11 sec squared theta minus 11. Then here we still have root 11 sec theta tan theta d theta. You can factor out 11 and the root 11. So basically you have 2 root 11 in the numerator over 11 in the denominator, then the square root of the integral, I mean, of sec theta tan theta over, in the denominator you now have sec squared theta minus 1, since you factored out the 11 there as well, d theta. Now, we do recall that 1 plus tan squared theta is equals to sec squared theta. So I want this one, sec squared minus 1. So you see that tan squared theta is equals to sec squared theta minus 1. So this is a trig identity. So in other words, in this integral, where we have sec squared minus 1, we can just replace with tan squared theta. So that our integral now, where we have sec squared minus 1, we'll just put tan squared theta. So the tan squared will cancel with 1 from here, leaving us with 2 root 11 over 11 integral of sec theta over tan theta d theta. So this is what we now have. Now, how do we integrate this? Is it something we can integrate? Well, let's look at it like this. The sec squared and tan squared can actually be combined a little bit. And what are we going to have? This is 2 root 11 over 11. So sec squared, we know sec squared is the same as 1 over cos theta. And tan is the same as sine theta over cos theta. And when you change the division to multiplication, you now have the integral of 1 over cos theta multiplying cos theta over sine theta. Here you still have 2 root 11 over 11. The cos and cos will cancel, so that now you're dealing with 11 and the integral of 1 over sine theta d theta. So now you just have to integrate sine theta with respect to theta. Now, how do you get the solution to this? Here, we can just recall the fact that we already obtained the integral of 1 over sine theta in the previous video. And let's see what we found when we integrated that one. So I think we did that one somewhere. It was the first example we did. Yes, here. So we did get the integral of 1 over sine theta. We used this same approach and it came out as, I think it ended up being this. So basically we used this substitution. The solution came out as this expression. So the solution came out to be this as the solution to the integral of 1 over sine theta. So once you have obtained it, you just have to now take back the theta, since you remember in this case, theta is not the original variable that we started with. So our original variable here was what? Let's see, we started with what variable? Our original variable was t, and t is connected to the previous one through that expression. Okay, so this is a lot of movement. We extract the variable. From t, we defined theta like that. And then theta is now what we're dealing with. Okay, here, let me see, am I coming from somewhere else? Oh yeah, we are actually coming from t. This is what we have. Started from here. Okay. I brought up theta again. So it looks like I mixed up the variables. I have to keep that in mind. From theta, I have to go back to t. And then from t, I have to go back to the original theta I started with. So be careful of mixing up the variables. Since I started with theta, I changed from theta to work with t. The next, perhaps best approach was not to use theta again. Perhaps I could have used u, so that when tracking back, I don't have to confuse them. But since I have already come this far, I can stick with the fact that I'm working with theta now, and then just make sure that from theta first I move back to t. Okay, so this is what my integral is going to be. So basically I'll have 2 root 11 over 11 and then multiplying this. So now this is the t, the recent t. I need to transform this from theta to the previous t. So since what I have here is tan theta over 2 in terms of t, what is this? So I'll go back to where I defined theta, which was here. So I want to express that in terms of t. So from here, I have sec theta being equal to, that's t minus 4 over root 11. So this is what I have here. Let me see, was that complete when I got that tan theta over 2? Yeah, it was complete. It ended there. Okay, so this is what I have here. This is not sine, this is sec. So I have sec theta is equals to that. So this, we know sec is just 1 over cos. So I have 1 over cos theta being equals to t minus 4 over root 11. So that in the end, cos theta is equal to, this is going to be root 11 over t minus 4. And since I now have for cos, I can easily get for sine. So here, I can easily get my triangle like this. If this is where my theta is, it follows that cos is adjacent, which is root 11 over the hypotenuse, making it t minus 4. Here, by Pythagoras theorem, the opposite has to be the hypotenuse squared, which is t minus 11 squared, minus the shorter side squared, which is 11 root 11 squared, making it just 11. So this is what this one is going to be. So that sine theta will have to be equals to the opposite, which is root t minus 11 squared minus 11 over t minus 4. Okay. Okay, yeah. Let me just make sure that is a 4. Okay, yes, that is a 4. So this becomes my sine theta. Then since inside here what I have is tan theta, or the half angle for tan theta, I have to recall the half angle identity for tan. Tan theta over 2, I don't want to start deriving the half angle identity. This is already long enough. Tan theta over 2, I know this is the same as sine theta over 1 plus cos theta. Or you can present it as 1 minus cos theta over sine theta. That's the same thing. So I'll go with the first one. So if I'm going with this one, all I need is where there's sine, I'll put what sine is. So in this case, where I have tan theta over 2, I am now using sine theta over 1 plus cos theta. And finally, in place of sine theta and cos theta, I will substitute what they are. Sine theta, we have all this. Then over 1 plus, where we have cos theta is this. Then plus c. So of course, this is something that you can express as a single fraction. Of course, let me do it very quick. It would simplify like this, so that in place of all this as a single fraction, we can present this as root of t minus 11 squared minus 11 over, here we have t minus 4 plus root 11. So that is what you get if you express it as a single fraction. Of course, you can go through this. I'm doing this very fast, so it's possible that I might have made a mistake here and there. Okay, so now that we have gotten rid of the theta and gone back to t, remember I have to go back to the original theta that was given in the problem. So here, this is where I define the second theta. Now I need to see how this t relates to the original theta. So again, it goes back to this. T is tan theta over 2. This is now what takes it back to the original theta that I had. So now I need to go back to my expression, and wherever I have theta, now wherever I have t, I'll now substitute tan theta over 2. So now just get this expression, and wherever you have t, put tan theta over 2. So once you do that, the answer you're going to get is going to be the final solution. So t shows up in two places, here and here. So in both places, put tan theta over 2. And what you'll get will be the final solution. I think this was just a little bit confusing because I think I ended up defining theta twice, as in there was theta which was originally in the problem. Then I redefined to t, and then I redefined to theta again, which was not supposed to be. Since I moved from theta to t, I was supposed to define perhaps a new variable u, so that when moving backwards to get that original theta, I was supposed to move from u to t, then to theta. That was going to be okay. But because I already went through this, I just described fully what I was doing. Otherwise, this is the solution that you end up reaching. But of course, this solution just depends on the substitutions that we decided on. For example, here we decided to go with a sec substitution. That was here. We decided to let this be sec theta. So if you choose a different approach here, you end up with a correct answer, but just that has a different structure. Okay, so let me know what method you used to work out this problem. Send me a solution if you would like to compare notes to 260979 38 20 81. Okay, I hope you found this helpful. If you'd like to see more videos of a similar case, let me know in the comment section. If you'd like to see my take on the other problems to do with this, and what other problems do you want me to work out next? Let me know in the comment section, or send them to that number through WhatsApp. Alright guys, see you in the next video.